Okay. Hello everyone, I'm Martino Russi from Hugging Face, and what I'm going to show you today is the HopeJr robot arm. It's a very cheap humanoid arm that we developed over the course of the past year, and the goal is to, lower the entry for robotics and especially for humanoid research applied to AI. So, okay. So just a brief, a couple words about the robot. By raising your hands, how many of you are familiar with the robot? Have you heard of the robot before? Okay, we have one, two, three. Okay, we have some people right there, and you can see outside. There's a couple of SO100 robot arms, which are our flagship product of the robot. It's a very popular library, and it essentially allows a seamless integration of robotics hardware and software, all done in a single Python library, which is quite powerful, and it's something that can only be done nowadays. So yeah, this is the arm that I was referring to. This is the SO100. And yeah, it's a 7 degree of freedom robot arm, and there's a variety of policies that are available at the robot that can be which allow one to run inference and training on this robot arm. Some of the more popular are, for example, ACT or diffusion policy and so on. So it's very cheap. This is the main point of the robot is to lower the entry for robotics. So we want everybody to have access to these robot arms, and just for people to train their own models without having too much of a hassle or without having too much knowledge of robotics. So yeah, and these are our flagship products. But this is not what I work on specifically. Oh, and there's also tutorials, of course, for assembly, and kits can also be ordered by Robo and SysStudio. So okay, that's enough of that. Yeah. So the reason why I got involved with the robot is a bit of a coincidence. So the main aspect of the robot is the open source. So we have open source arms, like the one I just showed you. And specifically, what I'm working on is open source humanoid arms and the teleoperation involved with them. So my study began by looking at the human hand. So the human hand is the most complex part of the entire human body. There's something called the homunculus, which is the cortical homunculus, which is essentially a region of the brain that basically shows how many neurons are dedicated for controlling each limb. And the astounding thing about the homunculus is how big hands appear in this topical map of the sensory motor cortex. So that's why I decided to study hands and to map their movements. It was mainly to get a lot of data from the brain, as these are the parts of the brain that move the most. So in terms of kinematics, hands are fairly simple, in the sense that like every finger has 3 degrees of freedom. So we have ulnar and we have ulnar abduction and adduction, and flexion for each finger. The thumb has 1 extra degree of freedom because we can also move the pip phalanx, which gives us a total of 16 degrees of freedom. These movements are then tracked by using a specific type of encoder, which I developed, which are called Hall effect encoders. So I didn't invent Hall effect encoders, of course, but using different types of magnets allows one to sense different regions of movements more or less accurately. So the principle behind these encoders is the Hall effect principle, and basically, if you have a magnetic field that is perpendicular to a current, the electrons that are running in the current will be displaced by a given amount, which will give us a voltage reading, and we can use that voltage reading to estimate the intensity of the magnetic field at that point. The nice property about this is that the change in voltage resulting from the Hall effect is directly proportional to the magnetic field. So basically, by increasing or decreasing the distance of a given magnet to our Hall effect sensor, which is the SS49E here, we can get a very good estimation of position and of angles. Yes. So as I mentioned, this is an open source. This is an open source project, and I would just want to spend a little bit of time in discussing how this developed and how this project came to be. This is not like a traditional research and development role, in the sense that the way this project originated was from just a hobby. So I developed this glove in my own time, and I fostered this community that was basically dedicated to researching and making this glove work in the most efficient of ways. And the way this comes to be is essentially people just join this community because they're interested in the glove, and then they just do work, and they help with the creation of new variants of the device. And it's quite fun. You get a lot of people. Some of them do work that is essentially useless. Like, for example, this person tried to make a glove out of popsicles. So like out of ice cream popsicles. And these people are always welcome, of course, and they contribute to the community in their own way. For example, then we have people who can make do with whatever they have available at home. For example, this person from India developed a glove using just components he had, like from a scrapyard. So just like magnets that he had available, and the Hall effect sensors. Yeah, and then there's other aspects. So, for example, once the project started gaining traction, we collaborated with Hong Kong University in order to develop this teleoperation kit for the Unity. And essentially, this is essentially a way in which you can achieve you can achieve teleoperation of robots, which wasn't even like my original intent. My intention was just to read activity from the brain through the hands. Well, but the main application that we found was in robotics, and this is what I'll be discussing later on now. Then we have another community member who made an upgraded version of the glove, which is the version that is open source, that we open sourced in May. And yeah, as you can see, basically these the way it works is just an exoskeleton that is positioned on the fingers. It has the same kinematics as the hand, and at every joint in green you can see there's the encoder modules that I mentioned previously. So yeah, and then I just wanted to talk about some of the more community members that were more impactful. So such for example, Max Titov from Guacadilla. He was the first one to actually try and replicate the glove, which is a very important step because many open source projects usually get no traction whatsoever. And it's only because of the community members that these projects actually take off and then become what they became today. And yeah, so essentially he used it for his bachelor's capstone thesis, and he basically made an upgraded version of it. And it was nice because there was this back and forth between us in the sense that like he would make an upgrade, for example, in the PCB aspect or in the design, and then I would copy that upgrade and sort of iterate on it. So, and it's a nice collaborative way of developing new teleoperation devices or robots, and so on. So now we get into so I developed this the glove that I just showed you independently, and once I open sourced it, and through Max, which is the person I just showed you before, I got in contact with Rob Knight, who was working on the humanoid arm at the time. So this humanoid arm had 23 degrees of freedom, and specifically it had 16 degrees of freedom in the hand. And that made for a nice coincidence because it meant that my glove could be used to directly teleoperate his humanoid arm. So, and yes, once we got invited to Humanoid Summit in 2024, we managed to connect successfully my glove and the DexHand, and that meant we could then, and that's where the collaboration with Hugging Face started essentially. So yeah, as I said, HopeJr is this humanoid arm that we developed at Hugging Face, and the main thing that should be noted is that it's tendon-driven. So there's not enough room in the fingers to actually place motors, or at least cheap motors, such as the ones that we're using by Fitech. And that means that one of the only solution that one can adopt is using tendons. So all the motors are placed in the forearm, which also lowers the total torque of the arm. And then these are connected through wires to the actual fingers, and that's the way that the fingers are pulled, essentially. This is the close-up of the hand that we worked on. So these are all the tendons, and they are pulled by these pulleys, essentially, that are placed in the palm and in the forearm. So yeah, this is just a commemorative picture. So we have Rami Kadin, who is the founder of the robot, and everybody else that participated at the summit. So basically, as I was mentioning earlier, the glove was just the first part. So once we managed to connect glove to hand, I also had to extend the teleoperation device to control the entire arm. It is quite fortuitous, the fact that HopeJr has the same degrees of freedom as the Unitary Humanoid, which means that the teleoperation kit that I developed can also be used for that purpose. And the main innovation, which was always in the spirit of keeping everything open source and modular and easy to replicate, was essentially connecting directly the SS40E sensors to these JST connectors, which then connected to a PCB, which allowed us to route all 16 signals through this PCB that we developed. And then the second innovation was also using two-hole effect sensors. So essentially, the magnetic field that you read from the magnetic field that you read from a diametrically magnetized magnet changes like sine. So in order to get accurate position, you can position the two-hole effect sensor at 90 degrees from each other, and then by computing arctan, you get like an accurate estimate of the angle of the specific joint that you're interested in measuring. And this is just some reading data from it. You can see it's quite accurate in the sense that there are you can read over 4,000 values in the span of 90 degrees, which means that it's very precise in terms of teleoperation. The second aspect we improved on was the rolling joints of the fingers. So we essentially, as I mentioned previously, the fingers are tendon activated, but there needs to be a way in which each joint of the fingers is connected to each other. And our approach was using rolling contact joints, but they have a problem in the sense that they dislocate quite easily. Which means that they need to be adjusted after every grasping task or manipulation task. The solution I proposed was simply locking these wires in place using screws, and that made for a very smooth motion without compromising the accuracy of the joints. The second aspect, which I hinted at before, was developing a PCB in order to route all these all the signal coming from the whole effect sensors together. So again, this was developed with the aid of the community, and it's quite nice to see like what you can achieve based on with so much collective effort. And yeah, essentially what we do is we just take a simple ESP32. And then we multiplex the signal so that every whole sensor is then routed to the USB. We then smooth out the signal using 0.1 microfarad capacitors, and that's the first version of the PCB. The second thing we did was then increasing the accuracy of the signal coming from the PCB, and the way yes. Sorry, just 1 second. Yes, okay. And the way we did that essentially is by using 3 op-amp. So we increase the voltage coming into the whole sensor in order to maximize the voltage range, so that it maxes out the ADC range of the ESP32. And the way we did that, as I was saying, is by using 3 different op-amps. One provides the signal, provides the voltage to the Hall effect sensor. The other subtracts the voltage so that the minimum is at 0. And then the third one just routes the signal back to the multiplexer. And what we get by doing this is essentially very precise teleoperation. So we have about 4,000 values of range. And so we then assemble these PCBs, and now they're freely available. So we open source everything. It's under HopeJr, so you can go and find both teleoperator and robot arm, and there's a BOM, and you can build this yourself essentially. So, and just to conclude, I'll just show some videos of HopeJr in motion. So this was done at C Studio, which is based in Shenzhen, and we essentially replicated collectively the HopeJr humanoid arm, and that took only about a day. So like it's a very quick and it's a very fast build, and it really doesn't take long. And yeah, so as you can see, that's the elbow that we're assembling. Then shoulder as well. And yes, so you can see this is the PCB with all the GST connectors that we routed together. Here we're assembling the fingers for the hand. And just a scene from Pacific Rim. And essentially the end result is, yes. So this is the teleoperation that we achieve essentially. So on one side we have the teleoperator, and then the SO leader and follower. And yeah, as you can see, the movements match pretty much exactly. And this was done in only a day. So yeah, so this is essentially it. This is the HopeJr robot arm, and it's open source. You can go and order all the parts required to assemble it.